Good morning to all. Today we will be discussing on growth techniques for nanomaterials, which is a part 2 section. So yesterday we were discussing about growth techniques for nanomaterials, and we'll be focused there on nanoparticles preparation and one-dimensional nanostructure preparation synthesis methods. Okay, and today, as I said, we will be focusing on the thin film side. That is a 2D nanostructure. Okay, for a 2D nanostructure, how do we synthesize and fabricate? So that we will be discussing today. Okay, so we'll start then. So as we said, 2D means two-dimensional nanostructures will be having. It will be like a plane, so that will be coating on a substrate. So such two-dimensional nanostructure we normally call it, examples are thin films, so which is of thickness less than 100 nanometer. Okay, so which will be coated on a substrate. So the substrate will be either a glass or any other material. So over that you will be coating a layer. Okay, so that layer will be okay, so it is basically thin films are the 2D nanostructures we call it as. Okay, and thin films, as I said, so it is a thin coating that will be coating on a substrate. The substrate, we can take any substrate. Okay, okay, there will be a substrate which we call a substrate. Okay, over this substrate we will be having a thin layer of coating, that is we call as this thin films. Okay, so we'll be having a thin coating, as you can see like here. Okay, so we'll be keeping a thin coating, so this is we call as thin film. Okay, so and this coating thickness, normally this thickness should be less than 100 nanometer. So any thin film, if you call a given layer of coating on a substrate is thin film, the thickness of the film should be less than 100 nanometer. Okay, so the thickness should be less than 100 nanometer, then you can call that layer coating as a thin film. Okay, otherwise you cannot call as a thin film, you can either call as a thick film if the film is more than 100 nanometer thickness. Okay, so that's one important aspect regarding thin film, because we need to understand how do we differentiate a thin and thick films. Okay, so the thickness should be less than 100 nanometer. That's a primary point in that regard. Okay, and now when how do we prepare this thin films? There are many methods to prepare thin films, thin coating. Like already you have experienced the kind of thin layer coating, like painting over your home, where you are actually using a brush and you can keeping a painting on a wall, and you will be getting a thin layer on your wall, right? So there are many methods. There's a very simple method that you can see, and also there's drop casting method is there, that is your uh, dropping a single drop of solution on a glass substrate, and you can in that method we call drop casting. And there is another procedure, it is a dip casting, that you are actually dipping your substrate. So you are actually dipping your substrate into the solution and you are taking off, and there will be a thin layer will be there. So there's in that all procedure you can see that in order to the layer to be coated on a substrate, there should be an process that is we call as adhesion. Right? So the probable atom should be adhesive to the surface that is dipping. Okay, so that is an important perspective when you talked about the thin film preparation. So the main preparation side you can see for the thin films are there, vapor deposition methods are there. Okay, so one is thermal evaporation method, another one is sputtering, and chemical vapor deposition methods are there. And also, as I said, there will be solution deposition method, where there you can observe self assembly is there, and electroplating is there, and spin coating is there. So there are many methods to prepare thin film preparation, and we'll see how the growth techniques on thin films will be working out first of all. Then we'll go to uh, different kind of preparation methods. Okay, so the one of the important one can see is that which we call it as epitaxial growth. Okay, so the epitaxial growth means you are actually coating a thin film on a lattice structure, and the orientation will be identical to the those substrate. So that means when you when you are coating on a silicon 10 substrate 100 substrate, okay, so the direction of the thin films, the thin film direction will be also aligned in that particular direction. Such films we call it as epitaxial films, and this thickness of the films will be very small in that case, and the epitaxial film will be take on a lattice structure. Okay, and the orientation will be identical to the substrate. For example, as I said, if you have a silicon substrate, okay, so Si100, if I specify 100 is saying the orientation of the lattice plane, and if you coat a thin layer of epitaxial layer, this will be order of less than 10 nanometer. Okay, the thickness will be order of less than 10 nanometer, and the orientation also, this thin film also will be 100. In such films we call it as epitaxial growth and epitaxial films. Okay, there are two type of epitaxial films are there. One is homoepitaxy, as you can see there. A crystalline film is grown on a substrate or a film of the same material. Okay, so a crystal film, that is we are making of, like if you want to coat a silicon on a silicon substrate itself, then that we call it a crystalline film is grown on a substrate or film of the same material. Okay, and heteroepitaxy means you are actually coating a crystalline film on a crystalline substrate or a film of different material. Okay, like if you have if you want to coat, for example, as I suggest here, if you have a silicon substrate which is which is already we know that it's crystalline. Okay, 10 direction, and now if you are coating another thin films which is of barium titanate. Okay, okay, if you want to coat barium titanate or silicon, so these two are two different materials. So such growth, such epitaxial film, we call it as heteroepitaxy. Okay, so you are coating on a different substrate. So so that is about heteroepitaxy. So this is one of the way you can actually grow on a lattice structure. Okay, ഒരു ലാറ്റിസ് സ്ട്രക്ചറുള്ള ഒരു ക്രിസ്റ്റലൈൻ ഒബ്ജക്റ്റിന്റെ മുകളിൽ നമ്മൾ എന്ത് ചെയ്യുന്ന ഒരു ഫിലിം കോട്ട് ചെയ്യുമ്പം സ്വാഭാവികമായിട്ടും ആ ക്രിസ്റ്റലൈൻ സ്ട്രക്ചറിന്റെ ഓറിയന്റേഷനിൽ നമ്മളുടെ ഫിലിംസ് വരികയാണെങ്കിൽ, ആ ഫിലിംസ് വരണമെങ്കിൽ അതിന്റെ കണ്ടീഷൻ എന്ന് പറയുന്നത് ഇറ്റ് ഷുഡ് ബി വെരി സ്മോൾ ആവുന്ന, അതിന്റെ തിക്നെസ് എന്ന് പറഞ്ഞാൽ വളരെ സ്മോൾ ആവുന്ന കണ്ടീഷനിൽ മാത്രമേ യു ക്യാൻ അച്ചീവ് ദാറ്റ്. സംടൈംസ് 1 നാനോമീറ്റർ 2 നാനോമീറ്ററിലൊക്കെ കേസ് വരുമ്പോൾ മാത്രമേ നിങ്ങൾക്ക് ഇത് അച്ചീവ് ചെയ്യാൻ പറ്റുള്ളൂ. അതല്ലാതെ നോർമലി ഇഫ് യു വാണ്ട് ടു ടേക്ക് എ ഗ്ലാസ്, ഒരു സിമ്പിൾ ഗ്ലാസ് എടുക്കാം. നമുക്കറിയാം ഗ്ലാസ് എന്ന് പറയുന്നത് അമോർഫസ് ആണ്. ഓക്കെ, ഒരു ഗ്ലാസിന്റെ മുകളിൽ ഇഫ് ഐ വാണ്ട് ടു കോട്ട് സം എനി മെറ്റീരിയൽ, ഫോർ എക്സാമ്പിൾ ലെറ്റ് മീ ജസ്റ്റ് ടേക്ക് എ കോപ്പർ ഫിലിം ഓവർ ഹിയർ. ഓക്കെ, സോ കോപ്പർ ഫിലിം എടുക്കുകയാണെങ്കിൽ, സോ ദിസ് ഇസ് ഓൾസോ യു ക്യാൻ ഡു ഇറ്റ്. ഓക്കെ, അതിന് നമ്മൾ എപ്പിറ്റാക്സിയൽ ഗ്രോത്ത് എന്ന് പറയില്ല. ഇറ്റ് ഈസ് ഓൾസോ എ ഫിലിം കോട്ടഡ് ഓൺ എ സബ്സ്ട്രേറ്റ് വിച്ച് വി കോൾഡ് ആസ്, ഗ്ലാസിന്റെ മുകളിൽ കോട്ട് ചെയ്തിട്ടുള്ള ഒരു ഫിലിം എന്നുള്ള അർത്ഥത്തിലേ നമ്മൾ പറയുള്ളൂ. വി വോണ്ട് സേ ദാറ്റ് എപ്പിറ്റാക്സിയൽ ഗ്രോത്ത്. എപ്പിറ്റാക്സിയൽ ഗ്രോത്ത് ആണെങ്കിൽ ആ ഒരു ലാറ്റിസ് സ്ട്രക്ചറിന്റെ മുകളിൽ നമ്മൾ എന്ത് ചെയ്യണം, ഫിലിം കോട്ട് ചെയ്യണം. സ്വാഭാവികമായിട്ടും അതിന്റെ ഓറിയന്റേഷൻ ആ ലാറ്റിസ് സ്ട്രക്ചറിന് അലൈൻഡ് ആയിട്ട് കൊണ്ടുവരാൻ പറ്റും. അപ്പം അതിൻ്റെ ഒരു ബെനിഫിറ്റ് എന്ന് പറയുന്നത് നമുക്കൊരു പെർട്ടിക്കുലർ ഓറിയന്റേഷനുള്ള ഒരു ഫിലിംസ് ജനറേറ്റ് ചെയ്യാൻ പറ്റും. അങ്ങനെ ജനറേറ്റ് ചെയ്യുമ്പോൾ നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും, അതിൻ്റെ പ്രോപ്പർട്ടീസ് ഈസി ആയിട്ട് ട്യൂൺ ചെയ്യാൻ പറ്റും. കാരണം പല പ്രോപ്പർട്ടീസ് എന്ന് പറയുന്നത് ഈ ഒരു ഡയറക്ഷൻ ഡിപ്പെൻഡൻ്റ് ആയിട്ടുള്ള മെനി പ്രോപ്പർട്ടീസ് ഉണ്ട്. സോ വി നീഡ് എ പെർട്ടിക്കുലർ ഓറിയന്റേഷൻ. നമുക്കൊരു പെർട്ടിക്കുലർ ഓറിയന്റേഷൻ ഉള്ള തിൻ ഫിലിമും ആ ഒരു മെറ്റീരിയലും ആ പെർട്ടിക്കുലർ ഓറിയന്റേഷൻ നമുക്ക് കൊണ്ടുവരാൻ എപ്പിറ്റാക്സിയൽ ഗ്രോത്ത് മുഖേന സാധിക്കും. സോ ദാറ്റ്സ് വളരെ ഇമ്പോർട്ടൻ്റ് ആണ് ഒരു തിൻ ഫിലിംസിന്റെ പെർസ്പെക്റ്റീവിൽ നമ്മൾ സംസാരിക്കുമ്പോൾ. നൗ യു ക്യാൻ സീ ഹൗ ഡു ദ ഗ്രോത്ത് മോഡ് ഓഫ് ഡിഫറെൻറ്റ് ടെമ്പറേച്ചർ. ഡിഫറെൻറ്റ് ടെമ്പറേച്ചറിൻ്റെ കേസിൽ എങ്ങനെയാണ് ഒരു തിൻ ഫിലിം ഒരു സബ്സ്ട്രേറ്റിന് മുകളിൽ കോട്ട് ചെയ്യുമ്പോൾ എന്തൊക്കെയാണ് അവിടെ സംഭവിക്കുന്നത് എന്നുള്ളത് യു ക്യാൻ ജസ്റ്റ് ലുക്ക് അറ്റ് ഹിയർ. Okay, so as you can see in the figure that is in the screen, the growth mode at different temperature. Okay, so initially the temperature is well below 150 Kelvin, and the growth mode is, you can see that you will not be getting a proper islands, and it will be not crystalline also, the deposition. So here you can see that we have coated some material on a substrate, and you can see these patches has been representing that the film is not properly crystallized. So it is like amorphous in nature, as you can see. And as the temperature rises above 150 Kelvin, you can see that 2D islands. So certain regions where the atoms are clustering, the depositions are clustering, so which we call the film depositions at different islands, different regions or some region of the substrate you can see. And now when you see up above 300 Kelvin temperature, then you can say that a clear 3D iron formation. That means it has a definite height. Okay, it has a definite height and a breadth, and of course lengthwise also it is there. Okay, so it is properly designed as a 3D island. When you take the 3D image of the island, then it will be you can see that above 300 Kelvin a definite 3D island is formed there. Okay, so this is an AFM image that is you are seeing here, so which representing growth modes at different temperature. So this is the atomic force microscopy image taken after annealing the or after growing the films at different temperature. Okay, hope you understood. So the temperature has a important role for the preparation of a crystalline films. Okay, for crystallinity we need to go for a temperature sometimes, or rather sometimes some materials will be crystalline in room temperature itself. So it is important to the temperature of to apply for the proper crystallization of the given system. Okay, so that I hope you understood that. And now when you see the growth kinetics, there are importantly there are three processes involved in the growth of a thin film preparation. So the important aspect is that first of all the particle that is you are depositing on a surface, and we should be adsorbed. Okay, it should be adsorbed on the surface and they diffuse around the surface, can bound to the surface. Okay, and the kinetics of epitaxial growth is already we said that it is by the surface diffusion and further the nucleation and the growth. So that's how the growth kinetics of the materials is goes on here. Okay, so the three processes are involved in the deposition of a thin films. So it involves the diffusion, nucleation and growth, as you can see here. Okay, so that's a three process one can see over here. Okay, so the particles are deposited on a surface and becomes adsorbed. Okay, and they diffuse around the surface and can be bound to the surface. Okay, now we see how do it happens. So we'll see a picture that is describing this process, as you can see here. Okay, when you talked about the process in atomic level, because we need to talk about atomic level, because here we are dealing with the epitaxial growth. So when it epitaxial growth, the thickness of the particle will be in the order of 1 nanometer, 2 nanometer. That you can say that if it is 1 nanometer, it is simply like 0.1 angstrom, right? Okay, so you can say in that perspective also. So here you can say that the atom is arrived on here, the R representing the atom arrival, and which will be surface diffusion will be there, and there will be also surface evaporation process, and there will be a binding of nucleus to the surface, and the nucleation starts here. So the nucleation process starts, and there will be, of course there will be a surface diffusion further, and it will be a rising on a layer. Okay, so this is actually a layer formation on a thin film. As the time progress, so the time quantity and the number of atoms arriving will be also increasing. Okay, and the things determining the energy of diffusion, the evaporation and the binding energy also demanding the determining the different process, and also the mobility of the particle that is coming to the surface. Okay, and also if there are some defects that is there in the substrate, then that is also affect the process of adsorption in the surface. Okay, it is not absorption, it is adsorption. Okay, those two are different. Adsorption is the process where the surface diffusion and the binding that is happening on the surface, and absorption we know it is a volumetric property. Okay, those two are different. Okay, that you also need to know, absorption and adsorption. Okay, now so when you talk this perspective in terms of atomic scale process, will be atom will be moving on the surface, and there will be the atom will be across the barrier as we suggested. Okay, so there is a atomic scale approach also to describe the process of surface adsorption, crystalline adsorption in a epitaxial growth. So it is involving, there is also bone formation and bone breaking, while the growth of phase growth in the sample. Okay, so that's the one thing we could notice while the atoms is getting adsorbed in the atom. So as you can see here, the atoms will be moving on the terrace. Okay, so the terrace means the surface at the first layer, and it will be moving across the 3D barrier. Okay, so this is a modeling basically it's a modeling of atoms that is coating over there, and which we call the terrace step string model method. So here you can see that it involves a bond formation and a bond breaking procedure in the event. Okay, so now we can see there are different type of growth modes are there, which is mentioned in different cases. Okay, here you can see that, as I said, there are different formation. ഒരു തിൻ ഫിലിം നമ്മൾ ഒരു സബ്സ്ട്രേറ്റിന് മുകളിൽ കോട്ട് ചെയ്യുമ്പം there are probably different way നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും, അതിൻ്റെ ഔട്ട്പുട്ട് എന്ന് പറയുന്നത് പല രീതിയിലായിരിക്കും കിട്ടുക. ചില കേസിൽ നമുക്കതൊരു ലെയർ ആയിട്ടായിരിക്കും നമുക്ക് അവിടെ ഫോം ചെയ്യുക, ചില സമയത്ത് അതൊരു സിമ്പിൾ പാർട്ടിക്കിൾസ് ആയിട്ടായിരിക്കും റിമെയിൻ ചെയ്യുക, ചില കേസിൽ അതൊരു ഐലൻഡ് ആയിട്ടായിരിക്കും എന്ത് ചെയ്യുക, അതിൽ നമ്മൾ ആ ഡെപ്പോസിഷൻ അവിടെ സംഭവിക്കുക. അപ്പോൾ അതിന് ബേസ് ചെയ്തുകൊണ്ട് we can see that there are three different modes. Okay, the first mode, which is actually there is an island formation. So the island formation means when you deposit a material on a substrate, it is simply forming an island where it's a region where you can only locate the materials in a specific region, and as the time progresses, as the quantity of deposition increases, you can see that there are many islands are forming. So this is the method of growth mode, which we called as Volmer-Weber growth method. Okay, Volmer-Weber growth method. And now when it comes to Stransky-Krasnov method, you can see that there is, of course, there is a formation of layer plus as an island also. Okay, there is all, as you can see here, initially we only having on a substrate we will be only having island. Now you can see here there is a first you can see a layer over here, and that over the layer you can see a islands. Okay, and as the quantity or the concentration as goes on, so you can see that the thickness of the island is also increasing. Okay, so there will be first layer formation, and further there will be a formation of what, there will be a formation of islands also. So layer plus island growth mode. Now if the thin film is growing like that, then that we call it as Stransky-Krasnov growth mode. Okay, and the third one, which we call it as Frank-Medium growth mode, where you can see that the first there will be a layer formation, and further the different step that is will be extending to the layer as it grows to the, initially there will be two layers, so two cross sections, and as the concentration increases, you can see that it is actually it is getting a layer on a layer on a layer, like a multi-layered structure will be getting, and this model we call it as Frank-Medium growth mode. Okay, Frank-Medium growth mode. Okay, so that is another type of growth mode what you can see on a thin film case. And as we suggested, the different process in a thin film growth, one can actually picturize like this. Okay, so it's involved the diffusion process, it involves the nucleation process, and it involves the growth process. That is the main three process that you can see in epitaxial films or any thin films. Okay, so here you can see in the figure the thin film growth process. Initially there is a single atom arrives, and this single atom is continuously coming and it is getting migrating, and as we have seen the re-evaporation of the atoms, and there will be a collision and combination of different atom on the surface, and there will be a nucleation process starts. Once the two atoms are collided, it can either combine, so that combination also will be there, and this combination will be resulting to the nucleation process, and there will be two or more nucleus will be produced in that, and this nucleation will be resultant to an island growth formation, and these islands will be forming on the substrate as you can see here. So it will be having a different shape on the island, and this again this island will be making coalescence, and it will be again combining each other, and there will be a layer formation is there, and there will be now we will be having a continuous film. Now there will be no difference of island formation. Now will be after coalescence there will be a continuous film will be forming as the time progress. Okay, so the thin film growth process, the important parameter is that one is the time is a very important parameter, and also the temperature also play important role. Okay, how much time you give a thin film to deposit, and it will take, so that is also important for a continuous film preparation. And also, so it is highly demanding for a property point of view. If any property point of view, the uniformity of the thin films is a very important perspective. The uniformity means over the entire region of the substrate, the film should be uniformly distributed, and the properties will be uniformly distributed also in that perspective. Okay, so that is an important perspective when you talked about the thin film side. Okay, now we'll come to the discussion, so that we were focusing on, so that is about the growth techniques of different growth techniques that is available to prepare thin films. So that is a very important aspect we need to discuss. The first one is on thermal evaporation. Okay, so it is about thermal evaporation, so that is the first technique we will be addressing here. So it is actually a vacuum chamber will be there, and we will be having a material inside, and by applying high voltage it will be just getting heated up, and it will be the temperature will be beyond its melting point, and the atoms will be in the getting evaporated, and if you place a substrate over above the material, then you can actually deposit that is on the substrate. So you can see the uh, representation of a thermal evaporation here. Okay, so here you can see that there will be a chamber. So this chamber will be a vacuum chamber, so we have to create a vacuum of the order 10 raised to minus 4 to 10 raised to minus 4. Okay, and by reducing the pressure inside the chamber, and the source materials is heated here. So we'll be by applying a voltage, we'll be heating up the material that is placed here, and once the heating, and the material will be getting evaporated once it's beyond its boiling point. Okay, and you can see that the evaporated content will be coming to the substrate that is placed over the top side. Okay, and there will be a crystal monitor in order to monitor the concentration and the size. Okay, and the source materials will be deposited on the substrate as you can see, and we can actually control the concentration of growth species in vapor. Okay, and the thickness will be measured in situ like by crystal monitor. Okay, and there will be also pressure monitor will be placed inside, and you can actually in this process you can actually get a material of the range from 100 angstrom to 100 nanometer range thickness material you can actually create. So it is a process where you can actually heating the material, and the evaporated material will be deposited on the substrate placed above the material as you can see in this figure. Okay, so this is a simple representation of the thermal evaporation process that is we will be utilizing in order to prepare the thin films. Okay, now we'll see the next method. Okay, so it is a simple description regarding the process of thermal evaporation. And now when it comes to sputtering process, the process is a bit different, and you can see here uh, so in the sputtering process, as you can see in the figure, we will be creating a rough vacuum. So again, like we'll be creating a vacuum inside the chamber. Okay, so the creation of vacuum is very important to avoid the most of the impurity particle and dust particle. And if you create a vacuum like that, you will be pure from most of the foreign particles that will be present in the chamber. Okay, and now we will be applying a high voltage to the chamber. Okay, so you can see that we have a target material. Okay, so we have a target material that will be placed here. This target means substrate target. Okay, now here in the down you can see that we have a wafer. Okay, and the sputtered ions also you can see here, and underglow discharge. Okay, so here what will happen is that we'll be creating a vacuum of the order of 10 raised to from minus 5 millitorr or something. Okay, and we'll be creating the vacuum inside the chamber, and further we will be introducing a argon plus. Okay, we will be introducing an argon gas, and we will be applying a high voltage plasma. Okay, and this wafer means the material you want to deposit. So this material will be placed over this wafer, or this wafer itself a material. Okay, so this while applying high voltage, it will create argon plasma. Okay, when because argon will be separated into Ar plus and electrons, and neutrals ions also will be there, and due to that there will be a plasma will be generating, and it will be generating a glow discharge. Okay, and this glow discharge process, the plasma will be accelerated Ar plus, in that the Ar plus ions. How do we accelerate to Ar plus ion? Because we will be applying a voltage across this wafer and target, and the wafer will be having a negative terminal, and the target will be having a positive terminal, and of course the Ar plus will be should be accelerated towards the target in that perspective, and it will be hitting on the wafer. Okay, and the neutral atoms of, if we have placed it on this wafer, if it is a gold particle, and this gold particles will be ejected due to the high energy air argon plus ions heating on the wafer. Okay, and the ejected atoms will be deposited on the target, which is placed above the material. So there will be argon ions. So when you apply when you introduce a argon ion into the vacuum chamber, then you apply high voltage. Due to the high voltage, the argon will be ionized, and this argon will be further by applying the voltage, it will be coming to the wafer, and it will be eject the gold particle or any material that is placed on the substrate material. Okay, and the material will be deposited on the substrate placed above there. Okay, and there will be, of course, in order to create the vacuum, we will be keeping a vacuum pump like diffusion pump we will be using, or other turbo pumps are there, where you can actually go fastly the to raise to minus 9 millibar order you can actually achieve in that one. Okay, so the sputtering, it is basically when you say that, it is actually the materials will be ejected from the wafer and will be deposited on the substrate. So that's the process we call as sputtering. Okay, now there is a another procedure in order to prepare the thin films, which we call it as chemical vapor deposition. And these methods, sputtering, chemical vapor deposition method, and the thermal evaporation method, which we call it as physical deposition method. Okay, so it's a physical deposition method, and there are solution based method which we call it as chemical deposition method, we call it as. Okay, so there are two types of deposition methods. One is physical deposition method, another one chemical deposition, and sputtering, thermal evaporation, and chemical evaporation will be comes under this material case. Okay. Now rough vacuum case. In rough vacuum also will be created again in the chemical vapor deposition method also. So here what we do is that we will be introducing the reactive gas inside the we will be having a substrate, the material target there that you want to deposit on the substrate. Okay, on that we will be introducing a reactive gas. It will be either oxygen or it will be either any other gas. It will be performing a chemical reaction in the gaseous phase on the surface, and the corresponding particle that will be ejected will be deposited on the chemical vapor deposition method. So that is also a nominal method that is many will be using for the purpose of preparation side. Okay, chemical vapor deposition method. Okay. So these are the two main methods we need to focus on, and also in addition to this one, as already we are shared, there are other procedures also there. That is spin coating methods are there. Okay. Hello. Okay. And also as I we discussed, there are few other methods also there which we call it as electrospinning and spin coating methods also there while talking about the solution deposition method. Okay, and this solution deposition method is actually you will be making the solution by using chemical synthesis method. Okay, then that solution will be dipping on the or dropping on the substrate, and we will be rotating by using the method. So in spin coating method, what we do is that we will be having a solution made up, and the solution should become a bit viscous so that to it in order to bind that on a surface. Okay, and now we will be putting a drop on the substrate and will be spinning will be spinning, that means we'll be rotating the entire substrate by using a motor or something. Okay, and while that we will be having due to the centripetal force with the material will be what it will be deposited on the substrate. So that's the one method that will be you can see while you talked about solution deposition method. Okay, so solution deposition method we can see that spin coating is a important method in that one. Okay. Okay, and yeah, so that's all about the preparation of thin films. Thin film preparation we already has been discussed. Okay. Okay, so that's all about the preparation of thin films. So its main important ones are sputtering, okay, and thermal evaporation, chemical vaporization. So these are the important process you need to address in that section. Okay, so that is important. So there are different steps are there. I just simplified the steps like creation of vacuum. Okay, and the further the uh, case. Okay, and also we have just said about chemical vapor deposition earlier also. So here it will be either you can use the laser over there, or rather you can use the same vacuum chamber in order to create the vapor deposition method also. Okay, so that's also there. So that's all about for today. So we'll be discussing only on thin film vapor deposition methods, especially thermal evaporation, sputtering, and chemical vapor deposition. And we also talked about how a thin film is getting adsorbed on a surface. Okay, how the thin film is gonna adsorbed on a surface. Okay, so that is already we have discussed. Okay, so with that I'll be winding up today's session there. Okay, next we need to discuss about different characterization techniques that is involved in the preparation of in the characterization of nano materials. Okay, so there will be talking about SCM, TEM. Okay, so many of such instruments there. Okay, so we'll talk it later on. Okay, with that, thank you.